Good morning everyone. Today we are going to discuss about BCD to XS3 code converters. First, what is a BCD number? BCD number is known as binary coded decimal we represent the BCD numbers with 4 bits. The BCD number is the BCD codes are self-complementary codes and the BCD representation is also called as 8421 representation. Next, coming to XS3. XS3 code, it is a non-weight code. It's a non-weighted code and it is a self-complementary code. Next, for converting the XS3 code, for converting the binary code into, for converting the BCD numbers to the XS3 code, we will add 3, that is 0, 0, 1, 1 to the given BCD number. For example, when we take a BCD number 4, a binary number 4, this representation in BCD is 0, 1, 0, 0, and when we add 3 to it, the 3 is 0, 0, 1, 1. If we add 4 to 3, that in the considering the BCD addition, 0 plus 1 is equals to 1. Here we get 1, and 0 plus 1 is equals to 1. So here also we get 1. 1 plus 0 is 1. 0 plus 0 is equals to 0. So here we get 1. This is the XS3 code for BCD number 4. That is, if we convert BCD number to 4, then we get a binary number, then we get 7. Next, coming to the conversion of decimal to binary. First, when we take a decimal number 3, we will have to convert it into a BCD number. So a BCD number is generally like binary number, so we divide it by 2, we get 1, 1. So BCD representation, binary representation of 3 is 11. But as a BCD number is represented by a 4 digits, So we add 2 zeros in the most significant bit. So we get 3's representation in BCD as 0 0 1 1, and for 5 it is, when we divide it with 2 we get 2 as a quotient and 1 as a remainder, and when we divide 2 with 2 we get 1 and 0 as remainder, so it is 1 0 1. And as it is a BCD, we have to write it in BCD representation. We will add 0 in the most significant bit, so which gives us 0 0 0 1 0 1 for 5. And now when coming for the truth table for it, we have decimal in one column, next BCD in one column, excess 3 in the other column. Now decimal number 0 1 2 3 4 5 6 7 8 9. Here we consider as the 0 0 0 0. We get 0 0 0 0 in BCD representation. Here there are 4 BCD variables: A, B, C and D, and we will get the outputs W, X, Y and Z for XS3. Here we take 4 variables, so we will get 2 power 4 combinations, that is total 16 combinations. In that 0 to 9 combinations are valid, because for a valid BCD number the range must be 0 to 9, and whereas for 10 to 15, as these are not valid BCD numbers, we actually do not care about the outputs we get with these. So now decimal number 0 is represented as 0 0 0 0 in BCD, and 1 as 0 0 0 1, 2 as 0 0 1 0, 3 as 0 0 1 1, 4 as 0 1 0 0, 5 as 0 1 0 1, 6 as 0 1 1 0, 7 as 0 triple 1, 8 as 1 triple 0, 9 as 1 double 0 1, and we have to convert these BCD numbers into now XS3 numbers. So what will we do? We will add 3 to the BCD number. That is, when we add 3 to the 0 0 0 0, we get 0 0 1 1, and when we add 3 to 1 we get 0 1 0 0, which is 4, and when we add 3 to 2 we get 0 0 1 0, and similarly when we add 3 to by BCD number 3 we get 6, that is 1 0 1, and for 3 it is 0 double 1 0, and for 4 it is 0 1 1 1, for 5 it is 1 triple 0, for 6 it is 1 0 0 1, for 7 it is 1 0 1 0, for 8 it is 1 0 1 1, for 9 it is 1 1 0 0. Now we must simplify this W, X, Y, Z using the K maps. For which values of, we must check for which values of A, B, C, D we are getting high, BCD number high. So when considering for W, we get for 5, 6, 7, 8, 9 we get high in W. And when considering for X, we get high in 1, 2, 3, 4 and 9. And when considering Y, we get high in the place of 0, 3 and 4, 7 and 8. And for Z, it is high for 0, 2, 4, 6 and 8. Now we will let us write here at a place. W is equals to sigma m of, this is representation of the min terms in SOP. W is equals to m of 5, 6, 7, 8, 9. So 5, 6, 7, 8, 9. Next, for X, 1, 2, 3, 4 and 9. So 1, 2, 3, 4, 9. Next, for Y, sigma m of 0, 3, 4, 7, 8. We get sigma m of 0, 3, 4, 7, 8. Next, for Z, m of 0, 2, 4, 6, 8. 0, 2, 4, 6 and 8. Now let us consider truth tables for W, X, Y and Z separately. Now when we consider it for W, consider it for W first. Here we get A, B, C, D, 0, 0, 0, 1, 1, 1 and 1, 0. As gray, K-map uses the gray codes. 0, 0, 0, 1, 1, 1 and 1, 0. For this is for W. Now for which values W is high? 5, 6, 7, 8, 9. 5, 6, 7, 8, 9. So here comes 5, 6, 7, 8 and 9. And the values for 10 to 16 are don't care. So we write X here, which is a symbol for don't care. Now we must group in K-maps in a way. First we have to check 32. Can we make a group of 32 ones here? No. So we go to 16. Can we make a group of 16 ones? No. So then we go for 8. Can we make group of 8 ones here? Yes, we can make. That is here. So we consider this as group 1. Next, can we make another a group so that group of 8 numbers, so that these are also included? No. So now we go to 4. Now we can group this 4 as a group, and we can group this 4 as one group. So this is G2 and this is G3. So now W is equals to G1 plus G2 plus G3. Now here for G1, this is the group. So as all are included in this upside, we will look here. All these are cancelled. Now when we look at this side, here we have 1 1 and 1 0. From 1 1 and 1 0, 1 is common. That means A. Next, in second group, this is second group. Here we have 1 1 and 1 0 in top. So from 1 1 and 1 0, 1 is common. So we write C. Next, when we look here, we have 0 0 and 1 1. From 0 0 and 1 1, 1 is common. That means we get B from it. Next, in G3, it's here, this group. When we check this group, we get 0 1 and 1 1. Then from when taking 0 1 and 1 1, we will take 1 as common. So we get B here. Next, when we check the top, we get 0 1 and 1 1. From that we get D as common. Now we can write this BC plus BD as, if we take B common, we get C plus D. So keeping this aside, this is the K-map expression for W. Now we must write the K-map expression for X. K-map expression for X. Here we write AB. Here we get 0 0, 0 1, 1 1, 1 0. Here we get 0 0, 0 1, 1 1, 1 0. Here we get CD. This is for X. Now what is the values for X where X is high? 1 2 3 4 and 9. So we have to fill it in 1 2 3 4 and 9. So 1 2 3 4 and 9. In the 10 11 12 13 14, in 10 11 12 13 14 15, and 10 11 12 13 14 15, we will place X as a symbol of don't cares. Now, is there any chance for grouping of 16 here? No, we don't have a chance of grouping 16. Do we have a chance for grouping 8 here? No, we don't have a chance for grouping 8 also. So now we go for 4 groups, grouping 4 numbers. By using the folding concept, we can group these two as a one group and this two as other group. So this group, let us consider this group as G1, and let us consider this group as G2, and there is no chance for grouping 4 elements, so that this one is included. So we will make a group of 2 numbers. Let us note this as G3. Now here X is equals to G1 plus G2 plus G3, G1 plus G2 plus G3. When we consider G1, we get 1 0 and 0 0 for this side, left side. from them 0 is common, so we write B complement. Next, when looking this top side, we get 1 1 and 1 0. From them 1 is common, so we write C here. And for group 2, we get 1 0 and 0 0. From them 0 is common, that means B complement is common here. Next, and when we see this side, we get 0 1 and 1 1. From that D is common. Next, when we check G3, group G3, we have 0 0 in the top, so we write 0 0 in the same way, that is C complement plus D complement. Next, 0 1 and 1 1 in the left side, so we get 1 as common, that means B, we get B here. Now we can write B complement C plus B complement D as, if we take B complement common, we get C plus D here. Next, we get B C complement and D complement. By De Morgan's law, we can write A complement into B complement as we can write A complement into B complement as A plus B here all complement. So here we have then here A plus B, C, A plus here, when we write here A plus B, that means C plus D here. So we can write B into C complement into D complement as B into C plus D complement. So when we substitute this here, we get B into B complement into C plus D plus B into C plus D complement. Now this is in the form of A complement B plus B. This is in the form of A complement B plus A B complement, that is XOR gate. So we get B complement B XOR with C plus D. Now this is the expression for X. Now we will go for writing, we will go for simplifying Y and Z. For Z, 0, the values of the places where the Y is high is 0, 3, 4, 7 and 8. 0, 3, 4, 7 and 8. So here we must draw the K map for it. First, draw the K map for it. 2, 3, 4, 2, 3, 4, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1 and 1, 0. Now this is the, we have to write it for Y, here. So for what values Y is high? Here it is 0, 3, 4, 7, 8. So we will write here 0 in the place of 0, 3, 4, 7, 8, 1, 0, 3, 4, 7, 8 we'll place ones, and in the place of 10, 11, 12, 13, 14, 15 we will place X as don't cares. Next here we cannot group ones of 32 ones, so we go with 16. We cannot group 16 also. Then we go for 8. We cannot group 8 also here. Then now we go for 4. We can group these 4 as one group and these 4 as another group. So this is a group G1, this is group G2. Y is equals to G1 plus G2. Now when considering the first group, as here all are included, we will neglect them, and this is the common this thing with A1. Here we will write A, B, C, D. So we will get C complement, D complement as output for G1, and for G2 we get CD. This is in the form of A complement B complement plus AB. This we can return this we can write as A XNOR B. That means C XNOR D. This is the output for Y. This is the output for Y. Now we must draw the K map for Z. While drawing the K map for Z, we have to use the same thing: 0, 0, 0, 1, 1, 1 and 1, 0. Here we get 0, 0, 0, 1, 1, 1 and 1, 0. Next in the place of 10, 11, 12, 13, 14 and 15 we will place X as don't, it is a don't cares. Next for Z, the values are 0, 2, 4, 6 and 8. So in the place of 0, 2, 4, 6, 8 we place ones. Here we must go with the same grouping concept. Here first we must check whether we can do a group of 32 ones or not. Here we cannot do a group of 32 ones, so we go with the 16 one, grouping of 16 ones. Here we cannot group 16 ones also, so now we will go with the grouping of 8 ones. If we fold this one, we can group these 4 and this 4, this total 8 as one group. So we get Z is equals to G1. Now for G1, as these 4 are included, we will neglect them this when checking this side, and in this direction if we see we have 0, 0 and 1, 0. From them 0 is common, that means we'll get D complement here. So from total if we write the, we got W is equals to A plus B into C plus D, and Y is equals to X is equals to B XOR C plus D, B XOR with C plus D, and y is equals to D, and z is equals to D complement. Now here we must draw the logic diagram for these things here now. So the logic diagram is first we have to take A, B, C and D. This is the A naught, A complement, B complement, it is C complement, it is a D complement. Now here Z is equals to D complement, so here we get direct Z as output. Next, when checking Y, we will get C XNOR D. So C, D as input for XNOR gate. This is the XNOR gate, so we get Y is equals to C XNOR D here. Next, now when considering for X, we will take B, C, we will take AND OR gate for C and D, OR gate for C and D, and we will take B for this and this. We will take an XOR gate, so here we get X as output, B XOR with C plus D. Next, when going for W is equals to A plus B and gate with C plus D. As we use the C plus D here, we can take the C plus D downwards and we can consider it here. So this is B and this is C plus D. So we must give an AND gate for this, and we must take the OR gate between this both, that is this output and A. Here we get W is equals to A plus B into C plus D. That is this one. Now let us check whether this is correct or not. Now we must consider a number, that is, let's consider 5 here. So the inputs for 5 is 0 1 0 1 ABCD format, BCD, and we get output as 1000. So here 1000 WX Y and Z. Now let us check whether this is correct or not. Now here the A value is 0, B is 1, C is 0 and D is 1. Now here we will get a D complement here, so this is where if the D is 1 we will get Z as 0, and here C one input is 0 and other input is D. As this is a XOR gate, for 0 and 1, if we take 0 and 1 as inputs, we will get 0 as output here. Next, for B, here the B is equals to 1 and here C is equals to 0 and D is 1. If we take here for the OR gate inputs as 0 and 1, then we will get 1 as output. And now here for this and for 1 and here the inputs for XOR gate are 1 and 1. So we will get 0 as output here in this case. And now finally this one. So one input is 1 and another input is B. So we will get output as 1 for the AND gate, and here the A is 0. So A 0. So the inputs for this OR gate are 0 and 1. So we get 1 as output here. So now W is equal, we got here in this we get while tracing this logic diagram, we get W as 1 and X as 0, Y as 0 and Z as 0. Now we got this the same way, we got the same thing here. So that means our logic diagram is also correct.